In this video, we're going to continue our discussion of condensed phases by talking about the force that dictates how those condensed phases are allowed to exist, intermolecular forces. This will be the first of two videos, with this video covering the main ideas of what intermolecular forces are and which of those forces we'll be interested in. There's a second video that talks about the impact that those forces have that you'll be watching next. Before we begin, let's start with a quick overview of the material we're going to cover today in this video. First, we're going to come up with a definition of what intermolecular forces are. We've talked about this definition a couple times so far this unit, but I want to make sure it's fresh in your minds before we continue with the topic. Once we identify what intermolecular forces are, we'll then dive into the forces you'll be responsible for this year. The first of which is going to be dispersion forces. We'll then move on to dipole forces, and then finally, one you might be more familiar with from your biology classes, hydrogen bonding. For each of these three forces, we are going to define what they are. We'll provide an explanation for why that force exists. We'll talk about the relative strength of the force compared to the other two. And lastly, we'll talk about ways in which you can look at a molecule and predict whether each one of these individual forces exists. To the right, you can see a diagram that hopefully looks relatively familiar. This is depicting the hydrogen bonding that exists within a sample of water. These dotted lines right here representing those hydrogen bonds. It's this interconnectivity, these things that hold these water molecules together, that gives water a lot of the properties we have and dictates a lot of the biology that happens in your body, which again is mostly water-based. So let's start then with a discussion of what intermolecular forces actually are. Intermolecular forces are an attractive or in some cases repulsive force that exists between all molecules within a sample. We're going to focus primarily on the attractive forces and the effects that they have, but repulsive forces are also part of what make intermolecular forces as well. These intermolecular forces are super duper important, but because they are the things that allow all substances to become liquids and solids. Earlier in the unit, we described liquids and solids as being materials where the atoms are significantly close together, whereas gases where the atoms and molecules are significantly further apart. To keep those things close together in solids and liquids, we need forces to hold the atoms next to one another, and the intermolecular forces are what do that for us. Without intermolecular forces, everything in our universe would be in the gaseous state all the time. Collectively, with the exception of hydrogen bonding, these forces are known as van der Waals forces. That might seem like a peculiar name, but you might also suspect that they're named this way because they're named after a scientist by the name of Johannes Diedrich van der Waals. Van der Waals was able to identify the existence of intermolecular forces by studying gases. Later in this unit, we'll talk about gases as having what we call ideal behavior. They act completely independent of one another. We have equations that describe gases based off of that assumption. Van der Waals was able to show that some gases behave in what we call non-ideal behavior. They don't follow the rules that an ideal gas does, and he theorized that this must be because there are some small attractive and repulsive forces between these individual atoms, and the ideal gas law theory doesn't take that into consideration. He was later able to develop equations and ultimately tools to measure and calculate these forces, and that's why we named these forces after him. So now that we've laid the groundwork for what intermolecular forces actually are, let's start talking about some of the individual forces that you'll be responsible for this year. The first of those three forces are known as dispersion forces. Dispersion forces are an attractive force between individual atoms that is caused by the momentary, the very temporary deformation of the electron clouds surrounding substances, and this deformation is caused by collisions between atoms and molecules. Now, that's unfortunately a relatively complicated definition. I'll have a diagram in a moment that I think will help clear it up a little bit. Before we get into the diagram, these forces are often sometimes referred to as London dispersion forces, and just like van der Waals forces, London dispersion forces get their name because they're named after a scientist by the name of Fritz London. He is a U.S. scientist, which is relatively uncommon in the discussions we have in our class. He was born in 1900, died in 1954. A lot of science before World War I and World War II happened in Europe, and that's why we reference a lot of Dutch scientists, a lot of Danish scientists, a lot of German scientists. Around that time, around the turn of World War I and World War II, during the industrialization of the United States, that's when we start to see a lot of U.S. scientists start to show up, and Fritz London was one of the earlier ones of those. those. Now that we've established what dispersion forces are, let's talk a little bit about why dispersion forces exist and hopefully clarify that definition from up above. Down below, we have a couple different examples of what we'll refer to as helium atoms. So we've got a helium atom here, and we've got a helium atom here. Now you'll notice this helium atom on the right looks very similar to how we normally expect helium atoms to look, generally spherical, whereas this helium atom over here on the left has a slightly funky shape to it. The reason this helium atom on the left looks peculiar is because it's been involved in a collision. Another helium atom has come in from another direction, traveling at a relatively high velocity. It crashed into the helium atom that we're looking at right here, and as a result of that, that collision has caused the shape of that helium atom to change. The electrons surrounding the helium atom got squished over to one side. More specifically, those electrons got squished over to this side of the atom. More specifically, those electrons got squished over to this side of the atom, making this side of the atom very temporarily negative because it's got all those extra electrons, and this side of the atom be very temporarily positive because it's had the electrons pushed away. If you've ever watched a video of a tennis ball hitting a wall at slow motion, it's the same exact thing that's going on here. When the tennis ball collides with the wall, it changes shape very dramatically just for a moment, and then the elasticity of the ball causes the tennis ball to snap back into its regular spherical condition. So the collision with another helium atom caused this temporary disturbance in the shape of the atom. And if you might have learned back from physics last year, this charge of positive and negative here is going to interact with the atom. It's going to cause the electrons in this atom to get pulled towards the positive charge of the neighboring atom. That's going to induce a second positive and negative side for this atom. That's going to match up with the positive and negative sides for this atom, and because these two atoms now have positive and negative charges, we're going to expect to see an attraction between these two helium atoms. That attraction is what our dispersion force actually is, and that's why we describe this attraction as being caused by collisions, and we also describe this attraction as being momentary or temporary. A fraction of a second after this collision and attraction occurs, the atoms are going to snap back to their normal spherical shape, and the dispersion force is going to disappear. The reason this force is still interesting to us, though, is because these collisions happen constantly, and millions and billions of them happen per second, the result being that even though it's very temporary, this is still a meaningful force when talking about attractive or intermolecular forces between atoms. Now that we've provided an explanation as to why dispersion forces exist, we can talk about their relative strength. You might already suspect this, but just to make sure that it's clear, we would think of dispersion forces as being typically very weak. And the reason they're very weak is because A, those forces are very temporary. They do not occur very often. They only occur for a fraction of a second. And generally speaking, but not always, the dipoles that are created, the charges, positive and negative, tend to be relatively small. Those collisions don't change the shape of many atoms and molecules very much. Last but not least, with dispersion forces, you need to be able to predict when dispersion forces will occur. And the great news is that this is super duper easy. All substances experience dispersion forces. If atoms can collide with one another, this deformation of the shape of the electrons can always happen, and the dipoles will be created and dispersion forces will exist. This, again, is an explanation for why all substances can be in the solid and liquid state. Without any intermolecular forces present, your substance will always be in the gaseous state, but because we always have dispersion forces, even if they're super duper weak, we can always get everything into the liquid state and everything into the solid state, given the right conditions. A great example of that would be helium and hydrogen, the two smallest atoms on the periodic table. Even though they tend to be gases under almost every condition, if you get the temperatures super duper cold, almost to absolute zero, you will get them to liquefy and you will get them to solidify. Last but not least, the strength of dispersion forces varies, and actually in this case it varies pretty widely, from very, very weak to actually relatively strong, and it's based on how easily these electron clouds can be deformed. And generally speaking, larger compounds and larger atoms deform more easily, resulting in stronger dispersion forces. You can imagine if if your atom is very squishy, if you can think about it, that's going to make the electrons move more when there's a collision, creating stronger dipoles, and it's going to mean those dipoles happen more frequently, leading to a stronger dispersion force. All right, we are finished with dispersion forces, which luckily is the most difficult of the three to describe. We'll move on to dipole forces next. Dipole forces, just like dispersion forces, are an attractive force, so we'll underline that first, between, in this case, permanent dipoles, such as polar compounds. I also have written ionic here. I'm actually going to cross that out simply because ionic forces, while still very much like dipoles, are a little bit different. So we'll stick with just the polar ones for now. These forces are sometimes also referred to as Keesom forces, and just like with van der Waals forces and London dispersion forces, that is due to the fact that there is a scientist by the name of Willem Hendrik Keesom, 1876 to 1956, that is primarily credited with the discovery and the characterization of what dipole forces actually are. The explanation for dipole forces is significantly easier than the explanation for dispersion forces. These are compounds that are polar, meaning they have permanent positive and negative sides. Those permanent positive and negative sides cause a natural magnetic attraction between them. The negative side of one polar compound is going to be attracted to the positive side of the other polar compound, and that attraction force is exactly what our dipole force actually is. It's the magnetic pull between the permanent positive and negative sides of polar substances. Again, we can talk about the strength of dipole forces. I would argue that the strength of a dipole force is determined primarily by the magnitude, which has to do with the value of the difference in electronegativity, so how polar something is, versus the number of dipole bonds. How many bonds in the compound are actually polar? So the strength can vary a little bit, but regardless of that variation, on average, dipole forces are stronger attractive forces than dispersion forces, and this hopefully should not come as too big of a surprise. In dispersion forces, they were temporary dipoles. They only existed for a fraction of the time. In dipole forces, the dipoles are permanent. Therefore, the force is always being exerted, resulting in a net stronger force. You might have also already guessed how to predict whether dipole forces do or do not exist, and it's entirely dependent on the polarity of the substance. To have dipole forces present, our substance must be polar. Therefore, if you want to predict whether dipole forces exist or not, you will need to be predicting polarity. I'm not going to go over the details of this, but if you recall from last unit, that means first drawing a Lewis dot structure for your compound, then converting that Lewis dot structure into a three-dimensional Vesper shape, looking up electronegativities of the individual atoms and calculating differences of electronegativities across bonds, and then finally predicting polarity using both the electronegativities as well as the symmetry of the molecule. In this scenario, this molecule, carbon tetrafluoride, is a non-polar molecule because of its symmetry, and as a result, we would not expect there to be dipole forces present in this substance. Wrapping this up, we can describe the fact that when we have more polar bonds present in a compound and those differences in electronegativities are larger, that's going to lead to stronger dipole forces. So let's start with a definition of what hydrogen bonding actually is. It's basically simply an extreme form of the dipole-dipole forces we talked about in the previous intermolecular force. And this extreme dipole attraction is caused by very large differences in electronegativities. If you recall from our previous chapter, this simply means that these compounds are more polar than most, and as a result, the electromagnetic attraction between them is stronger than most. And that's what we're saying down here. The electromagnetic attraction between these very polar compounds is almost as strong as a bond. That's how strong we're talking about here, which is why we refer to this type of bonding as hydrogen bonding as opposed to just a regular old force. Moving on to our explanation for hydrogen bonding, over here we have a diagram that depicts a bunch of water molecules that are hydrogen bonded together. We can see in the picture that we have our regular covalent bonds here drawn as the bold lines, and the hydrogen bond drawn here as this dotted line, and it's showing these two water molecules attached to one other water molecule. This is that intermolecular force at play. What makes hydrogen bonding unique and different from the other intermolecular forces is that this attraction is so strong that it's similar in strength to this attraction here. And this oxygen atom really doesn't necessarily see a huge difference between this strength and this strength. As a result, there are conditions where this oxygen atom will actually start sharing electrons with this here, creating this into a covalent bond, causing this bond over here to break. Well, this thing here, this bond formed here, causes this bond to break as well and to turn instead into a intermolecular hydrogen bonding connection. And as you can see, once we start doing this once, this is going to start causing these changes to happen throughout this network of hydrogen bonded together water molecules. So what you end up getting here is that a hydrogen bond and a covalent bond are so similar to one another that atoms actually start flipping back and forth between the two of them over and over and over again. This is what creates this exceptional attractive force that makes hydrogen bonding unique from the other intermolecular forces that we've talked about. As you might suspect, when we start talking about the strength of hydrogen bonding, we can think of hydrogen bonding as being the strongest of our three intermolecular forces. It's almost like having a regular covalent bond. Because this force is so strong, hydrogen bonding is the force we look to that causes the largest changes to the properties of a substance. In our next video, we'll talk about the effects that intermolecular forces have on properties. We're going to be looking to see hydrogen bonding as being the one that causes the most significant changes. Last but not least, we have to talk about how to predict whether or not hydrogen bonding will or will not occur. For hydrogen bonding to exist, we have a couple conditions that have to be met. First of all, your substance must contain a hydrogen atom, hence the name hydrogen bonding. And that hydrogen atom has to be bonded to one of the following, either nitrogen, oxygen, or fluorine. It doesn't have to be all three, any one of those. The reason these specific elements are involved is because, if you recall, nitrogen and oxygen and fluorine are the elements with the largest electronegativities of all the elements on the periodic table. Those super high electronegativities are going to create the big differences in electronegativity when bonded to hydrogen, which is going to create those superpolar conditions needed for hydrogen bonding. Wrapping it up, the more of these types of bonds, these hydrogen to nitrogen, hydrogen to oxygen, or hydrogen to fluorine bonds that are present in your compound, the greater the interconnectivity is going to be between your molecule. If you have more than one of them, you'll be able to form 2 or 3 of these types of connections as opposed to just one. And then taking that one step further, this leads to a stronger effect that the hydrogen bonding will have in your properties. So not only does hydrogen bonding affect the materials the most, but having more hydrogen bonds present is going to affect those materials even more. And that's it for this video. Basically, we just outlined what these different types of intermolecular forces were and how to identify them was our big idea. You should be able to define all of those terms: intermolecular forces, dispersion, dipole, and hydrogen bonding. You should be able to identify the relative strengths that the intermolecular force has compared to the other intermolecular forces, which is very simple, but also compared to itself. In each case, we talked about different scenarios where a particular intermolecular force might be stronger or weaker, just like we talked about with having multiple hydrogen bonds just recently. You should be able to make those comparisons as well. Last but not least, you should be able to identify what intermolecular forces are present in any given compound. I should be able to give you a formula. You'll do things like Lewis dot structures, Vesper shapes, and polarities, and from that you'll be able to identify whether or not there are dispersion, dipole forces, or hydrogen bonding. In our next video, we're going to talk about the effect that these forces have, and you'll need to be able to make these types of identifications to answer those types of questions.